Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, yeah, it's a pleasure to have Thomas tell us about the scheduling problem, which is, I guess, one of the three or four remaining open problems from Garey and Johnson. So the problem is really old, and Thomas is going to tell us something new about it.
Yeah, thanks. I think technically speaking, we're not going to completely close it. But anyway, yeah, thanks for getting up so early. No, this isn't the time for everybody in the room. Okay, yeah, this is.
There's only 5 of us in the room, so you could talk to us a little more personally.
Okay, I will try to address the audience more personally. Thank you, James, for asking the first question before I start. Okay, so this is joint work with Elaine Levey, who is also at UW. Okay, so this is the problem I want to talk about. You have some unit-sized jobs. So you have some jobs that have processing length 1, and the jobs have precedence constraints. So you have to process, let's say, this job before you can start any of those jobs here. And I give you m machines that are all identical. And now the goal is you want to schedule the jobs in a non-preemptive way so that the makespan is minimized, and the makespan is the time that the last job finishes. So, okay. Okay, so just to warm up, let me just explain you a simple 2 approximation algorithm that's now 50 years old, and it works as follows. You just schedule everything greedily. So let's say you just select any job that you can select, and you just put it on one of the machines. Now, there's another job that you can just process. And now you see that, in principle, you have a third machine here, but you don't have a job where all the predecessors are already completed. So you leave that slot empty, and you move on with the next time and with the next job. So you just do everything greedily the way you would imagine it makes sense. So this is how the algorithm would work. And okay, so here you see that, there's this chain. We didn't pay a lot of attention to that. So we have quite some idle times here. And now this is the time that the last job finishes. You can see that actually this is the makespan here. So this is the time that the last job is finishing. You can also see that this is not the optimal solution. There's this chain of 5 jobs. We probably should have started this a lot earlier and just work on the chain all the time. Yeah, but this is an approximation algorithm, and it definitely does not always give you the optimal solution. But the claim is this gives you a 2 approximation. So how can you see this? So first of all, if you stare at the times where there is some idle time, where you didn't use all of the machines, then why did you do that? Why did you not process this job earlier? Actually, the reason is that there has to be a job that it depends on coming earlier. And that's actually the only reason why you couldn't schedule this earlier. So to be more precise, there is a chain that goes over all of the non-busy times. And if you wanted to be formal, you could construct this chain from the last job. You could wonder, why did I not schedule this guy earlier? Well, because of this job. Why did I not schedule this guy earlier? Because of this job. Why did I not schedule this guy earlier? Because of this job, and so on. Now you can wonder, if you have a chain, what's the length of the chain? Well, the length of any chain is the lower bound of the optimum, because also the optimum kind of needs to process the chain somewhere. Okay. So that's good. So this gives us a bound on the non-busy periods. Actually, bounding the busy periods is even easier, because you can imagine that even if the optimum would be allowed to ignore all the precedence constraints, even then, just to process all the jobs, you need at least that amount of time. Okay? Good. So, and now you just add things up, and you get that the schedule we're getting has length at most 2 times the optimal. Actually, the algorithm isn't much better than a 2 approximation. You can be a little bit more careful, and depending on how large your number of machines is, you can be a little bit better than 2. But if that number goes to infinity, then the ratio goes to 2, like the approximation ratio of this algorithm. Okay. So we would like to beat this algorithm, and it's kind of what's like the standard technique in approximation algorithms. It's you write down some linear program. So we could do that. And this might be the natural linear program. Like experts would probably call that the time index version. So let's say you have a variable xjt, and this variable is going to tell you whether you want to run the job at time t. And I hope you see that you only need to consider integer times. They're just integer time slots. So what would be the constraints? Like every job should be scheduled somewhere. At any time, you can schedule at most m jobs. M is the number of machines you have. And then you should have some constraint that implements the precedence constraints. So you should have, if some job I should be finished before j, then it's kind of the fraction that's finished until some time t can't be bigger than the fraction that's scheduled for that other job until time t plus 1. Okay, and good. So this is a fine linear program, but can you beat the gap of 2? No, not really. It's not hard to come up with some integrality gap construction. Just imagine in this case, I give you 2 machines, but you could have some kind of blocks of 3 jobs. Let's say this is like a long sequence of jobs, and it's kind of all the jobs in the ith block depend on the I minus first block. And now the fractional solution that you could construct would be that you can kind of process all the jobs in the same block in parallel. And so this would mean like these 3 jobs in an integral solution, you would need 2 time units, but the fractional solution could essentially schedule this in 1.5 time units. It's nice to observe that in the fractional solution, the support of jobs can overlap even if the jobs have precedence constraints. So this is something you can't rule out. That makes the whole thing difficult. So the integrality gap, it's also essentially 2. So if the number of machine grows, then the gap will tend to 2. So this isn't really going to buy you that much.
Is it a rounding algorithm based on this?
You could probably come up with some rounding algorithm. I doubt that you could beat the simple greedy algorithm.
But even getting factor 2.
It's for this problem, it's extremely hard to not get a factor of 2 in some sense. So yes, it's probably an exercise. I haven't done it myself.
Is it the same as integral scheduling, but you allow me to start jobs at fractional times? I mean, that's at least what this takes advantage of, right? Like 1, 2, and 3 start at second 2, and then they go to second 2.5, and then you start 4, 5, 6. I'm just saying then you sort of can, at least for this, you can respect the precedence constraints, but just have, be able to.
Is this the same? I don't think so. No, I don't think so. I don't think it's the same. Okay, good. Okay, so we did see that little 2 approximation algorithm by Graham, and in fact, it's unlikely that you can beat the 2 in general. So there's a paper by Ola saying that, well, under some variant of the unique games conjecture, you won't be able to beat the factor of 2. Then now there's the question what I'm going to talk about in the next 2.5 hours. But okay, so in scheduling, it does actually make a lot of sense to consider cases like what happens if the number of machines is a constant. So think of m as being a big constant. Maybe then we can beat the factor of 2. And there hasn't been much success, actually. So this is what we want to do. OK. And Mohit mentioned already that this is essentially one of the 4 open problems in Garey and Johnson, though now it's maybe 3.5 open problems, now that graph isomorphism is kind of solved.
I'm confused. You can beat factor 2 if m is a large constant. So what's the question? You put it there.
If m is allowed to grow with the input length, you can't beat 2.
Okay. So how are you going to fit a result in between those 2 bullets? That's what I was.
I will give you an algorithm, but the running time will depend exponentially on m, on the number of machines. And there was no such algorithm known before. That's better than 2. OK. OK. Good. So in fact, if you have, let's say, 3 machines, it's unclear whether this is an NP-hard problem. There's a nice survey of Schurman and Wöginger about open problems and scheduling. It's now 16 years old. A couple of problems have been solved. One of the problems that has been open is whether, let's say, for 3 machines, there is a p-test. And
so is there for any constant hardness node or no?
It's not, no.
For any constant, yeah.
Like if you have 10 billion machines, it's also open whether this is NP-hard. Yes. And the result I want to talk about here is that actually you can take that linear program, you can throw it into your favorite LP or SDP hierarchy, and after some number of rounds, the gap goes down to 1+epsilon. That number of rounds is a weird number that's a little more than polylog. And the epsilon and the m actually goes here into the O. OK. So this gives you also an algorithm that finds the schedule in some kind of weird, a little more than quasi-polynomial running time.
But the dependence on n is like pretty big. That's because you didn't write.
That's like the rule of thumb. No, there's an m. It's really an m here, and I think times 1/epsilon square, I think, is the dependence here. But on the other hand, it's in the exponent, so yeah, good. OK, good. So this is what I want to talk about. OK, so yeah. OK, so what's the Lasserre hierarchy? The idea is it's a very general idea. You imagine you have some linear program, let's say with binary variables. Let's say the set of feasible fraction solutions is k. And now you want to add in some more constraints so that your LP becomes better. So what you would ideally want to have is that convex hull of the integer points in k. Yeah, you're not going to get there. But you can write down some bigger system, and it's going to be kind of stronger than your original linear program. That system will depend on some parameter that's called the number of rounds of the hierarchy. And as you increase the parameter, the hierarchy gets stronger and stronger. And then eventually, after number of variables, many iterations, it's going to converge to the integral hull. OK. So many of you might have seen this already. So the idea is that if this is just a general linear program, then and t is your number of rounds, then you would just take variables for all subsets of at most t many variables, and you write down some kind of meta variable, which is supposed to tell you the extent to which all of those variables have to be 1. So you have some xr variables. This is why it's also called lift and project, because like the xr variables, they give you a lift. And in particular, you will have your original variables in there. And now you just need to write down some constraint system that gives you some kind of consistency. And you can do this explicitly. It's not, I don't want to go into details. At this point, I would like to treat the Lasserre hierarchy as a black box. We know what properties it has. But if you wanted to write down explicitly the constraints, then you would take your variables, you would throw them into a big matrix that's called the moment matrix, and then you ask that this moment matrix has to be positive semi-definite. You also will take all the constraints that you have, and you would put them together into another big moment matrix, and also that has to be positive semi-definite for any constraint.
Why you say it works with Sherali-Adams?
Yes.
So why are you describing the Lasserre?
Purely hypothetically, imagine one of the authors has a survey on the Lasserre hierarchy and wanted to copy-paste the sections. I find the definition more elegant than for Sherali-Adams. It doesn't matter. So we're using, the Lasserre hierarchy has a lot more power than we need. Okay. I hope that doesn't cause you a headache. Okay? We're not using any kind of fancy like polynomial whatever power here. Okay? Good. James doesn't look convinced, just for the record. For the people who can't see.
I'm trying to follow, so I want to be prepared for.
Okay. Imagine this is Sherali-Adams, and you can just imagine for yourself this is Sherali-Adams. It's not going to be any different, the algorithm itself. Okay, so if that number of rounds t is a constant, you can solve those systems in polynomial time. And well, for us, it's not going to be constant. It's going to be that like weird, somewhat more than polylog term. So this is going to be, a little more than quasi-polynomial. Okay, good.
Okay, I have one more question. So if 2 minus epsilon was NP-hard, then your result says that the running time of the reduction, like assuming that, like say SAT requires exponential time, your thing says the running time of reduction has to be at least something.
Yes.
Do you have any idea of like ballpark what that is, or it's just like some function of epsilon and m?
Yeah, it's going to be some function. I never figured out, but you could have some argument in that. Yes. Yeah. Okay. Okay. So the Lasserre hierarchy and the Sherali-Adams hierarchy, they have some nice property, which is as follows. If you look at a solution which is valid for t rounds, then and you look at one of the variables that's strictly between 0 and 1, then it is true that this is actually a convex combination of two solutions, two Lasserre solutions, one where the variable is 0, one where the variable is 1, and both of those are valid for one round less. Okay. In particular, a way to reinterpret this is as follows, that if you have a Lasserre vector, you have a variable that's strictly between 0 and 1, then you can say, oh, I want to have that this variable is actually 1. So you can you can induce on that variable being 1, which geometrically means you're just replacing your Lasserre vector by one of those guys where the variable is actually 1, and this is going to cost you 1 round. Okay. And we will do this frequently.
1 or 0?
You could do this. Yeah, we're doing this with 1. Obviously, the same thing would also work if you wanted to set the variable to 0. Yes. Yes. Okay. Good. There's one observation that's worth making. That looks trivial. But if you do this conditioning, then the support of your Lasserre vector is only going to shrink. Now, if you, imagine this would be an actual probability distribution. And if you induce on some event, then another event that had a 0 probability before is still going to have a 0 probability. No conditioning will make the probability suddenly positive. Okay? Good. Okay. Fine. So this is, let me now go to the algorithm. And, so here's a little bit what we're going to do. So imagine we kind of guess the time that the optimum needs. Let's say this is capital T. So imagine this is the time horizon. We kind of give this parameter capital T to Lasserre, and we find some Lasserre solution with a large enough number of rounds, which is kind of valid for that scheduling LP. And now we want to round that scheduling Lasserre LP, STP. Okay. So first, let's, OK, if this is the time horizon, let's look at some kind of a binary partition of that time horizon. So we just partition everything always into two intervals of the same length. And then, like, obviously, OK, we need like log t many levels. And now let's imagine that these are jobs. And let's look at the support of jobs. So these are the times where the Lasserre vector has some positive probability of scheduling the guy. Okay? So they don't have to be intervals. They don't need to be consecutive, the support. OK. Now we want to do the following. Imagine, for the moment, we kind of assign the jobs to the minimum interval containing all the support. OK? Now the idea is we want to have an algorithm that essentially starts at the bottom of that partition and schedules the job. So we would like to first schedule the jobs that have a very small support, and then later add in the jobs where the support was very long. Okay? Kind of hoping that they had more flexibility. Okay. Good. Okay. Now this is the actual algorithm. This is the overview over the actual algorithm. In the first step, we do the following. We look at the first, let's say log n square many of those levels. And we massage the Lasserre vector by conditioning on certain events. We will get that the maximum chain of jobs that are assigned to those levels is small. And I will explain this a little bit in more detail on the next slide. Let's take this as given for now. OK. Now, after we do this, let's say these are the supports of the jobs, and these are the intervals where they are assigned to. Yes?
Sorry, I missed something very basic. What does it mean, the support of a job?
These are the time units. These are the time units where this guy is scheduled. So let's say this is JT, where this is positive. Okay? Imagine this is the support of a job, and now kind of with respect to the current Lasserre solution.
Is it clear the support will be contiguous?
No, it's not in general.
Okay, so your figure seems to say.
The laziness of the person drawing the picture, which is me, suggests that it would be. OK, I think one's here. Yeah, and then from now on, they just look like intervals, but they don't have to be. Yeah. OK, good. OK, so so it's like, for example, like this blue rectangle means that, yeah, there's some probability that the job is scheduled here, some probability that the job is scheduled there, and so on. OK. Good. So now we want to create some gap here. And we take log n levels kind of somewhere in the middle, and we delete all the jobs. OK? We throw them away. Now, you might be saying that I'm forced to schedule all the jobs. But if I have a small fraction of jobs that I kind of threw away, I can kind of just insert them at the very end. And you can just imagine that for every job, you can just insert a private new time for him, and you can just insert him. And that is, well, you just pay this extra in the Makespan. But that's not a big problem. OK, so as long as we're throwing away only an epsilon over m fraction of the jobs, we're good. OK, good. Now, this creates a gap in the sense that now the intervals at the top are a lot longer than the intervals being down here. And if you do the math, then actually this factor is like a polylog term of this thing. And I need that polylog term. That's why I have log n levels here. OK, good. Now I do the following. I have my Lasserre vector. And please remember that I did some conditioning. So it's not anymore the original Lasserre vector. But I do the following. I now recursively run my scheduling algorithm, and I schedule all the jobs in those bottom intervals. So I go through every of those bottom intervals, and I just schedule the vectors. I schedule the jobs, and I do this independently for those intervals. The important thing is that I have my Lasserre vector, and I give a copy to every of those intervals here. And now, since I do this recursively, there's going to be some conditioning going on here, some independent conditioning going on there. So I schedule the jobs.
Sorry, how do you schedule the jobs?
Recursively.
What does that mean?
Well, to understand recursion, you first need to understand recursion. Yeah, it's an old one.
So you're,
Sorry.
So you're doing that, using that property that every point is a convex combination of.
I would say
That's
here.
what you mean?
Okay, the algorithm that I kind of here described, I described it here kind of for the top interval, for the largest possible interval, for the whole time horizon. But you can imagine you run the same algorithm that I just described here. You run it just for that smaller time horizon, and you run it only with the jobs that had the complete support in here.
But they're not exact solutions, right? Because I only schedule a job to a fraction inside that.
Wait. I look at the jobs that have the whole support in here. And then it looks like the original problem. Okay? It's just on a smaller time scale. Okay. Okay, good. So that looks fine. But there's a problem. So there are my top jobs. And now I also have to schedule the top jobs. And the problem is I kind of have to insert them in the gaps that remained. And there isn't really a reason why this should work. And so what could be the problem? The problem is that we're doing a lot of conditioning and in the Lasserre solution, and this is not necessarily consistent. So it might be that in any actual integral solution, it's like if you schedule this job at the end, then in the other interval, you would have to schedule another job kind of at the beginning, so that, or also at the end, so that you can schedule those top jobs in between. So there is some consistency that we are losing. Okay? But it will still be enough. And why does it work? The reason is that we have decreased the length of the maximum chain among the top jobs, the jobs that are assigned to the top intervals. Okay, good. Okay, so first things first. Let's start about the first point. What did I want to do? I had those jobs that were assigned to the first poly-log n many levels, and I wanted to decrease the length of the maximum chain by conditioning on certain events.
So Thomas, I just want to get some intuition. Is it clear if all the chain lengths are small, you have a simple p-task or something? Because I don't understand.
Yes, it is.
Okay, so is that
because just look at Graham's algorithm. Okay. The bound here is essentially you get the optimum plus the length of the maximum chain, which is that itself is bounded by the optimum. But if you give me a better bound on the length of the maximum chain, you can get something better than 2. So in particular, from this, you already see that you only have a major problem if you have long chains. So we're kind of getting rid in some sense of the long chain problem. Well, they will still exist, but yeah. Okay, so where were we? We were precisely not here. Okay, this is the thing. Okay, so don't look at the statement of the lemma that we're going to prove. Look at the picture. So imagine this is one of the top intervals, and imagine there are a ton of jobs assigned to it. What does it mean they are assigned to it? It means their whole support is contained, but the whole support also kind of contains the separating line between the next subintervals. And okay, now imagine it happens that some of these jobs has a lot of other jobs dependent on him. So in this case, there's the blue job, and let's say there are a lot of other jobs dependent on him, but still the support can overlap. This cannot be ruled out. Okay, Now we do kind of the obvious thing. We spend one of our Lasserre rounds, and we condition on the event that this job with the high out degree is scheduled in the right-hand side interval, in the right-hand side subinterval. Now, after this conditioning, all the other jobs that depend on him will also be fully scheduled in that right-hand side interval. So in some sense, after one conditioning, the support of a lot of jobs actually moves down by one level. Okay. And so now, well, you just repeat this argument, and the support of jobs always moves down. You do this often enough. You count how many intervals do you actually have among the top intervals, and then you get bound on the number of rounds that you're losing. So there's some little calculation, but it's this is the basic argument.
So again, I still did not get this condition, etc. Right? So if we know the current fraction solution, I can write as a convex combination.
Yes.
Either it is completely scheduled in I2 or not at all.
Yes.
So you want to say either I'll go here or here.
Yes.
How can you just say I'll just go here?
You take one of the variables and you condition it to be 1.
Yeah, but the conditioned fraction solution might not be a good fraction solution. It might have a large objective.
I don't have an objective.
It's a feasibility problem.
It's a feasibility problem.
Okay, good.
Okay. Any other question? Okay. Good. Okay. So I hope. Okay. What I hope I could convince you is that I could actually, if you look at the picture, I can actually decrease the maximum chain length of jobs assigned to the top intervals to something, well, as small as I like. Okay, and that number, well, I will lose some number of rounds proportional to that, but I'm good. Okay, good. Okay, so that's fine. But okay, yeah. Let me go back to the next thing that we want to do. Okay, so after I recursively scheduled all the jobs assigned to bottom intervals, now the crucial argument is how do you insert the jobs assigned to top intervals? And now the only thing we know is that actually the length of any chain among those jobs is very short. It's as short as we like. Okay, now let's move on with that. Okay, so where's actually the problem? Imagine this is a job assigned to one of the top intervals, but the job may actually depend on some jobs that are scheduled in bottom intervals, and it also may have some of those jobs dependent on him. And the problem is that now we would recursively schedule this guy somewhere in this interval, but maybe we'll schedule him at the end. And we might schedule this guy somewhere here, but maybe we'll schedule him at the beginning. So we don't have any control over that. So in principle, I can imagine that for my top job, the only way to be safe is that I insert him in some slot that comes after the end of any interval where a dependent bottom job was scheduled. Okay? So I could imagine that I define a release time for this job, and this is some kind of scheduling term. I define a release time for this job, which is the end of any interval where a dependent bottom job is scheduled, and I define a deadline for my top job, which is the beginning of any interval where, like the earliest interval where a dependent bottom job is scheduled. Yeah. Okay. And now, I will try to schedule my top job somewhere between that release time and deadline. And if you look at the support of the top job, there's a little bit of a problem because there's some fraction of its support where I'm now kind of forbidden to schedule the job. Okay? Good. Okay, but here's the claim. Now, the point is that the bottom intervals are a lot shorter than the top intervals, and the gap is some polylog term. Okay, and I want to essentially schedule the top jobs imagine in two phases. In the first phase, I want to just prove you that I could schedule the top jobs if I would be allowed to ignore any precedence constraint other than that I have to schedule the job between release time and deadline. This is what I show in the first phase. In the second phase, I show that, okay, now imagine I know that I can schedule the job between release time and deadline if I ignore precedence constraints. Now I can also schedule it with precedence constraint, knowing that the precedence constraints that I have to respect don't have long chains. Okay, so let's start with the first argument. If the top jobs wouldn't have any precedence constraints with each other, what could I do? I claim that then I could actually find a good assignment. And now this is an easy problem. This is essentially a bipartite magic problem, where you can imagine that for every top job, there are some time slots where you could schedule the job. And you know that the Lasserre solution, it was a fraction solution for that bipartite matching problem. The only difficulty is that there are some parts of the fractional solution are cut off. Now, if you have a matching problem and there is some part in the matching graph that's cut off, but you can check Hall's condition and you can just see what is the amount of edges that I'm losing. And okay, so essentially the only thing you need to check is the following. You look at some subset of the top jobs and you lose what is the neighborhood, what is the size of the neighborhood you're losing. And now the argument is that that out of Q intervals, out of Q bottom intervals, you're only losing 2 intervals. You're only losing the slots in 2 intervals. And the reason is that every of the top jobs must contain one of those borderlines. And you know that you have one of those borderlines only every Q of those small intervals. Okay? So in particular, it means that you cannot lose more than 2 bottom intervals in any of that are contained in one of the top intervals. And I'm not convinced that this was a great explanation, but I hope you believe that this is not a hard argument. So this is essentially, it's a bipartite matching problem. You can bound the number of jobs that you can't schedule anymore by just looking at Hall's condition and just counting by how much your neighborhood could possibly shrink. And here you use that, well, you're kind of talking about intervals. Okay? Good. Okay, so this is the first phase. Now, the second phase is, might look familiar to you if you're into scheduling. Essentially, we're using the earliest deadline first scheduling policy, which is kind of, it's a standard thing in scheduling. It's kind of optimal in many settings. It's not exactly optimal in our setting, but it's good enough. Okay, so what is the problem? Now, imagine these are our top jobs. These are the jobs assigned to top intervals. And now what is the setting? What do we have left now? We know that the length of the maximum chain is not too long. We can make this as small as we like. We know that, well, each of those jobs may have a release time and may have a deadline. But we know that actually the time horizon is partitioned into a not too large number of blocks which correspond to where the top intervals begin and where they end. Sorry, where the largest of the bottom intervals begins and ends. And we also have some capacity left. And please remember that we already scheduled all the bottom jobs recursively, so there are some slots are left. So you can imagine that there's some kind of capacity curve, and we have to fill in the top jobs somewhere in the remaining slots. And from the last slide, we do know that if we would be allowed to ignore any precedence constraint among the jobs, we would be able to schedule everything. Okay, and now the argument is that, well, we can still schedule essentially all of the jobs, losing only a small number. And here the crucial argument is that the length of the maximum chain was bounded. Okay, good. So what is the earliest deadline first algorithm? You essentially sort the jobs according to their deadlines, and now you just schedule them greedily. And let's imagine the following. If you have a job and his deadline is coming and we didn't manage to schedule the job in one of the slots, then we just throw it away, and we want to count how many of the jobs did we throw away. Okay, and there's the last slide. And this is essentially a modification of a standard argument in scheduling. So if you ever look into a scheduling book, you might find something very similar. So imagine this is the time horizon. These are blocks, and you only have deadlines at the beginning and at the end of those blocks. Okay. Now let's assume, for the sake of contradiction, that there's some interval where we have discarded more than k many jobs, and we want to get some bound on k. So let's imagine this is very, very large, and then we will come to a contradiction. Okay, good. So for some technical reason, imagine that the last job that you discarded in this block, it really was the lowest priority job. And imagine you just delete everything else. The trick is that the earliest deadline first policy doesn't actually change for all the jobs that came earlier. So that's without loss of generality. Okay, so we know that this block is kind of overloaded. For some reason that we don't understand yet, we were throwing a lot of jobs away. Now let's backtrack, and let's see. Let's go back to the last block where we had less than c many idle times, and c was the bound on the maximum chain length, meaning that actually the block before had more than c many idle times. And now the crucial argument is, if you have a job that we did schedule in one of those blocks here, then I claim that the deadline could not have been before this point. Because if it would have been before this point, then it would have been at this point or earlier. And I had more than c many idle times, meaning I could have scheduled him here. So the point is, the observation you should make is, okay, so let's say in this picture, the maximum chain, okay, imagine the maximum chain length is 2. And now here, let's say I have three free slots. Now imagine you want to schedule a job, and you want to schedule it as early as possible. Then the only reason why I cannot schedule him in one of those 3 slots would be that, well, he has to depend on this guy. But why did I not schedule this guy earlier? Well, he has to depend on this guy. Well, then he has to depend on this guy. So then you can, again, construct a chain of length more than c, very similar to Graham's algorithm, to the analysis of Graham's algorithm. And then you would get a contradiction. OK. So what happens? So every job that we actually scheduled in this area, it had release time and deadline here. So it had and any of those k jobs that we couldn't schedule, it has release time and deadline here. And that gives you a bound on k. And the bound depends on c and that number of blocks here. Yeah, I think it should be, k should be bounded by PMC. And so you know that in no block you discard more than that many jobs. So you probably have to multiply that with another factor of p, which is your number of blocks. And that's actually the end of the whole thing. Okay. So there are some calculations. You just need to count how many jobs did you throw away in total. You choose the parameters correctly. But every idea is actually you did see. Okay. Is there any question? Okay. There are actually some open problems. So it's not so clear whether not a constant number of Lasserre rounds would be enough, or Sherali-Adams rounds, or at least an actual polylog number of rounds. So for us, this is like log. This is m divided by epsilon squared times log n. So that's not so nice. Actually, also a nice problem is what happens if you have running times that are not 1, but you have arbitrary running times. Some of the arguments still make sense, others don't. So that would be nice whether one can have some extension here. And yeah, that's what I wanted to tell you. Thank you for listening.
Questions? What's known for the problem?
For this one? Well, the 2 approximation. So Graham's algorithm also works if you have general running times. 2, maybe 2 minus 1 over m, something like that, but nothing better.
Yeah. Any question? I had one technical question because it might be doesn't make any sense. But somehow you just like, why did you need this break of log n? Because I thought you just needed it to break. You just need q to be large, right?
Yes. Yes.
But q could be a large constant as well, right? Okay, it depends on epsilon. Why does it need to depend on n?
Yeah. Okay. The problem is like how many jobs do you throw away? So you want to say you want to throw away like an epsilon or epsilon over m fraction of jobs throwing away would be fine. Yeah. There is a technical problem, which is that the level where the jobs are assigned, it can move because you do the conditioning. And this makes it very hard to only cut a constant fraction of the jobs. So this is why we had to choose the parameter larger. Yeah, it does look like a technical problem. We really thought for some time about it, but we couldn't get rid of it. Yeah, that's the reason why there's the log n to the log n term. It's one of the things where you write it down, you think, okay, it's not going to take you more than 20 minutes to find a solution, and 2 weeks later you say, let's be happy with it. Yeah.
Any more questions? Okay, not less than Thomas again.